Welcome everyone to the IFIMAC plus ICMM seminar series on condensed matter research. Thank you all for being here today. I'm Laura Arriaga from Universidad Autónoma of Madrid, and I will be the chair of this seminar. So before introducing our speaker today, let me remind you how we usually proceed in these seminars. If you have any question during the talk, please write it down in the chat and I will interrupt our speaker and ask on your behalf. Otherwise, please wait until the end of the talk so that you will be able to unmute yourself and ask directly and talk to our speaker. You can let me know by using the right hand button or writing in the chat. And now it is my great pleasure to introduce you Professor Esther Amstad from the École Polytechnique Fédérale de Lausanne, who is going to tell us today about droplets and how to use them for making hydrogels. Let me tell you a bit about Esther before giving her the floor. She studied material science at ETH in Zurich. She did her PhD also at ETH under the supervision of Professor Marcus Textor. During that time, she worked on surface modification and steric stabilization of oxide nanoparticles. Later, she joined as a postdoctoral fellow the group of soft condensed matter of Dave Waits at Harvard University. And there she became an expert on droplet microfluidics, designing very novel and amazing devices for producing many drops and very small drops, the spray dryer. And since June 2014, she's at TPFL in Switzerland, where she is now an associate professor, and she is leading her group on soft materials. So Esther, please go ahead, the floor is yours.
Thank you very much, Laura, for this nice introduction and giving me the possibility to talk to you through, within this seminar series. It's a real pleasure for me to be here.
In Russia, there is no longer
a lot of the inspiration that, of the research that my group does comes from nature. And not, I mean, of course, many groups do that because nature manages to produce materials that display a set of properties that is unique and which we still cannot mimic with man-made synthetic materials, despite that we have many more elements available that we can make our materials from, and we can vary processing conditions over a much wider range than actually nature can. And here are just 4 pictures of materials on top 2 soft materials, namely the fibers of the Mussel byssus, which are these 100 micrometer diameter threads that allow muscles to firmly connect to solid surfaces. Spider silk, which I think everybody of you is familiar with. And on the top, there is 2 hard materials, nacre, as well as teeth of some mollusks, which are extremely stiff, but yet tough at the same time. Now, the question is why? Why can nature do that and we cannot? And to me, this was a question that actually fascinated me since I started studying science. And within this talk, I'd like to keep asking this question over and over again and try to make some analogies to the Mussel byssus, which again is this thin thread here, which is made out of protein. So it's a polymer-based thread that displays an exceptional combination of strength and stiffness. And this is shown or nicely illustrated, I think nicely illustrated here, where you see such a muscle that is firmly connected to a stone that weighs many times the weight of the muscle itself. Yet if you lift the muscle, you don't break the threads, you don't break the connection between the soft threads and the hard stone, which would usually happen in synthetic materials, but instead you lift the stone together with the muscle. Yet if you relax, you put everything down, you see that these threads, they bend, and actually if you would apply shear, which typically happens in the sea where these muscles usually are, when they are attached to rocks or ships, you would realize how tough they are because they don't break even if you apply very high shear forces to them. Now, if you compare it to a material that is usually used to mimic this kind of Mussel byssus, which is hydrogels, polymeric networks filled with water. You can tune the mechanical properties of these hydrogels over a very large range, and you can make them very soft, flexible, but if you pull on them, well, they just break because they're too weak. Or you can make them extremely stiff, so they can bear significant loads, but as soon as you apply a little bit of torque on them, well, they catastrophically break because they're very brittle. And so the holy grail would be to combine stiffness and toughness. Why? Because then you could use them for load-bearing applications, and you could leverage the unique features of these hydrogels to actually actuate them or leverage their response to different stimuli, which is something that nature can do, but we just cannot do because we can make responsive hydrogels, and we can do that with a very good precision in terms of responsiveness, but they're usually just far too weak to bear any significant load. And to put that a little bit more into numbers, I tried to summarize the stiffness of synthetic hydrogels that we can make, different types of hydrogels here plotted as Young's modulus versus the toughness, which I plotted as the tensile strength here. And you can see that we can vary these parameters over a wide range. They vary in composition of these composition and structures of these hydrogels, but we cannot get to this nearly to the same combination of stiffness and toughness that the Mussel byssus, for example, displays. Similar things would be true, for example, for the cytoskeleton as well. And so for this reason, we just cannot use, however, hydrogels for certain areas like soft robotics or as tissue replacements because they're too weak. Instead, we use them mainly for moisturizing applications in food, very much so, as contact lenses in tissue engineering, but all applications where you need these materials to retain a lot of water, but not to bear any significant load because they're too weak or too fragile. The question is why? Why can nature produce such functional soft materials? Why we fail to do so? And I think one of the answers to this question lies in the structure and the local composition. If you look very closely at this Mussel byssus, and again, I take the Mussel byssus as an example, you'll find many more of these kind of materials in nature. But if you look at the Mussel byssus, you basically see that it's made out of very different materials and structures. It's all protein-based, but here you have proteins that self-assemble into liquid crystalline smectic liquid crystalline structures. There you have low regions that are basically purely covalently cross-linked, and other regions that are purely ionically cross-linked. Then you have a shell that has a completely different composition and structure, and yet you have a plaque, the adhesive part, that yet has another decomposition and structure, as you see also in these scanning electron micrographs here. And I think really the combination of this very precisely controlled local composition as well as structure on different length scales in the end allows nature to build these kind of high performance soft materials. Whereas if you look at hydrogels, the way that we synthesize them, while we can tune the composition with a very high precision, we can to a certain extent control structure, but only over very limited length scales. But if you then look at the composition and structure as a function of the location, you realize that most of them are homogeneous and they have some sort of a ill-defined structure. Okay. Now, that is a bit of a shame, I think. And the reason, the question is, why cannot we do better in terms of controlling local composition and structure? If you think about how you control these parameters, it often comes back to how these materials are made, the processing. And if you look at how nature produces these kind of high performance soft materials, you see a striking resemblance between the formation of these fabrication of these different soft materials, and that is that most of them are somehow fabricated from compartmentalized reagents, reagents that are produced prefabricated at very high concentrations, and then stored within well-defined compartments. And whenever nature wants to produce these materials, these reagents, these compartments are released, reagents are locally released, and that allows nature to control local composition and to locally non-linearly vary it, and to a certain extent also to control the structure over very different length scales. Now, That is a bit provocative, but if you think about how we make our synthetic hydrogels, we basically mix and match reagents in both. And that gives us a very good control over the overall composition of our materials, but we just cannot control local composition or structure of these materials, which would be required, I think, to bring this technology to the next level. And so as a result of that, well, we can, again, vary the stiffness here and the amount of polymer contained in our hydrogels over a wide range. But this is a summary of stiffnesses of 3D printed hydrogels. You see that they're all very soft. So we talk about 10 to 100 kilopascal. And if you remember, the Mussel byssus is tens of megapascal. So there is orders of magnitude in stiffness that we just miss. And so this is, to a large extent, where Micro takes inspiration from to design more advanced soft materials that hopefully in the future can combine the mechanical properties and incorporate functionalities that natural materials actually do, but we just fail to do so with soft materials. And I hope that throughout my talk, it becomes clear that we are by no means there I think we should be, but I hope it also gives you an idea as to how I would like to tackle this question and challenge. Now, the goal really would be to make materials that are stiff and tough, but in addition, that are functional, such that they, for example, can locally stiffen if stressed, heal if broken, or release reagents if needed. To get there, of course, we don't start from scratch, and a lot of very, very nice work has actually been done in the lab of Dave Waitsby and Laura and I met on the encapsulation and the control of the composition and dimensions of these capsules that enable you or that allow you to control when and where things are released. More recently, more advanced containers have been demonstrated where you can encapsulate different types of reagents within one container and then conduct chemical reactions within these confined volumes, or you can also use them for sensing purposes or incorporate them into materials to render them functional, for example, self-healing. But what is common to all these applications that the capsules, the particles, are basically used as individually dispersed entities to deliver reagents or to functionalize materials. Instead, if you look more closely what nature does in terms of material fabrication, it doesn't use them as individually dispersed entities, but uses them collectively as building blocks of larger structures. And I mean, to me, a bit surprisingly, this concept has only been introduced into soft materials in a consistent way about 5 years back, where microparticles made out of hydrogels have been up-concentrated and then 3D printed into granular materials. And these granular materials are increasingly often used for tissue engineering because they have a quite well-defined and porosity that allows exchanges of nutrients, maybe even cell penetration into these systems. Now, the problem is just if you 3D print these kind of microparticles into granular materials, they often retain their shape, but they're extremely weak because the particles are very weakly connected to each other, mainly through physical van der Waals interactions. This, of course, this weakness has been recognized by the community, and a lot of different strategies to link different microgels together have been introduced, including host gas chemistries, covalent cross-linking through their surfaces, or through ionic interactions. But if you go through this literature and you analyze how these connections actually influence stiffness and toughness of this granular material, at least I was very surprised because, well, maybe these connections help to increase the stiffness by a factor 1.5 or so, but not by more. So all of these materials are still very, very weak, such that you cannot really use them for any load-bearing application. Now, once I started thinking about it, well, one of the possible reasons for this weakness is that basically these particles are spherical, so their contact area is very small, and then that means that the interparticle connection, the density of this connection is also very, very low, such that I think this is the reason for the softness of these materials. If you just have very few bonds, even if the bonds are strong themselves, like covalent bonds, you still get a weak material overall because of the low cross-linking density. So again, if you look at the stiffness as well as the toughness, you're in a similar range as before, as the range I showed you before, 10 to 100 kilopascal Young's modeling. So how can we do better? How can we increase the stiffness and at the same time increase, or at least not decrease, the toughness of these materials? And to answer this question, I actually divided the work of my group into 3 different parts. One is the fabrication of these capsules or particles of the individual building blocks. One is their processing into macroscopic granular materials and the interparticle connection to transform these materials into low-bearing materials. And the third part is on the functionalization. Now, for time reasons, I'll only talk about the first 2 topics within this talk. Again, starting from what's well known in literature, and a lot of this work actually has been done while I was a postdoc in the lab of Dave Waits, we use still double emulsion devices. Double emulsions are nothing else but small aqueous drops typically that are incorporated into a larger drop, in this case, oil-based drop, that is dispersed in a third fluid. So you have water, oil, water systems. And actually, this is a device that I introduced together with Laura in the group of Dave Waits. And that allows you to produce these kind of double emulsions with well-defined dimensions and relatively thin shells at reasonable throughput. So we could make about 1,000 drops per second. Now, if you want to use them as templates to make these capsules in a controlled way, you basically you make them and then you solidify here this shell. To make the life of my PhD students a bit convenient, so what I wanted to have is double emulsions that remain stable for a couple of hours, so you can produce them, collect them, and then translate them into capsules without being exposed to too much time pressure. And so I thought, well, let's be smart and take an oil here that has a very low solubility. All the reagents that we are interested in, which are hydrophilic, have a very low solubility. So we took a fluorinated oil. Sorry. And so I asked my first PhD student, one of the first experiments that I did as an independent researcher, to actually incorporate some fluorescent labels within these double emulsions and see how long they remain inside. And I thought, because these fluorescent labels have almost no solubility in this oil phase, they'll stay there forever. Sorry. But what you actually observe is that depending on the exact composition and concentration of the fluorophores, they leaked out within a couple of minutes to a few hours. And that was a bit of a problem for us, because then we didn't have any control as to what and how much of things we have inside. And if things diffuse in, you can assume that things diffuse out. If reagents diffuse outside, you can assume that things that are in the outside diffuse in. And so we have no idea actually what is again in the shell and in the inside. So we had to somehow solve this problem. And around this time, there was a very nice article published by a colleague from Paris that did a similar study, but on single emulsion aqueous drops in oil, where he claimed that reagents are transported between aqueous drops by the formation of inverse micelles, that the surfactants actually, that are composed of the surfactants that we use to stabilize these emulsions. So these surfactants form inverse micelles and carry the hydrophilic reagents across oil pieces. And so I thought, well, if that happens for single emulsions, that most likely will happen here as well. And that is the reason that everything is released. So how can we suppress that? And there was a couple of iterations going on. And initially I thought we could suppress that by tuning the surfactant composition, but it turned out that this was just not the right way to go. And so I asked the student to make a very simple experiment to take basically this oil with the surfactant, once in contact with air and once in contact with the aqueous phase. And if you closely look, what we saw is that here at this interface, you have increasingly objects that start to scatter light. But objects that start to scatter light must have a dimension that is similar to the wavelength of optical light, so 100 nanometers. Much, much, much larger than any of the micelle can be. So in our systems, the formation of micelles to me just didn't really add up to what we see. And so we did some, in collaboration with some friends in Poland, we did some fluorescent microscopy analysis, and we saw that actually micrometer-sized aqueous drops formed at the oil-water interface. So somehow we had a spontaneous emulsification happening in the oil phase that most likely will also happen in the oil drops. And so the question was, well, if that hypothesis that we have a spontaneous emulsification happening at this interface is the reason for the transport that we see, then actually the transport of the reagents across these oil phases should scale with the interfacial tension, because this is the energy you need to pay to form these small drops, right? The higher the interfacial tension is, the energetically more expensive it is to form these drops. And so we synthesize different types of surfactants, all have the same type of blocks, but we vary the length of the hydrophilic block and thereby the interfacial tension. And what we could see is that actually, yes, the leakiness, which we measured as the time needed to reduce the fluorescence of the core by 50%, linearly scales with interfacial tension between the water and the oil phase. Here we varied the concentration of the surfactant. Here we varied the type of surfactants that we synthesize, that we use. And so to me, there was a possibility to suppress that was to actually reduce the mobility of the surfactants to prevent them from absorbing from the interface and forming these small drops. Yet I didn't want to covalently cross-link them, because if you covalently cross-link them, you form a rather rigid shell that if it breaks, it's broken and the capsules become leaky. So there again, we took inspiration from nature, from the Mussel byssus, but this time from the adhesive properties of these mussels, which comes from a molecule called Catechol, which looks like that very strongly binds to certain ions, such as iron. And we thought, well, maybe we could use this molecule here to reversibly bind our surfactants at the interface of the drop. So we synthesized these functionalized surfactants, and we stabilized the emulsions with them. First question was, does this in functionality here that we introduced actually already allow us to suppress this fluorescence? And to test this, again, we use fluorescein in the core. We stabilized the emulsions with these surfactants without ionically cross-linking them. And we looked at the fluorescence. And what we saw is that actually, in this case, the transport is very strongly dependent on the pH. If the pH is like 10, where these hydroxy groups are deprotonated, so actually the surfactant is negatively charged. And if you look at the fluorescein, this is deprotonated as well, so it's negatively charged as well. The two molecules repel each other. We basically had no transport whatsoever or a very long time. By contrast, if we lowered the pH such that these molecules, the surfactants, were neutral, uncharged, and some of the fluorescein was charged, some was uncharged, well, we got the transport, and the transport was even lower at pH 4, where both molecules were uncharged. So this to me indicated that actually charge or the attraction between the two molecules, so the encapsulants and the surfactants, somehow influence this transport. But the question was, is it the charge of the surfactant, or is it the interaction between the encapsulant and the fluorescent and the surfactant? And to answer this question, we encapsulated a different dye, a dye that is actually positively charged at high pHs and neutral at lower pHs. And there we saw exactly the opposite. When the high pH, where this surfactant, the fluorophore was positively charged, the surfactant was negatively charged, so you had an electrostatic attraction between the two molecules. We saw a very rapid, almost instantaneous transport of almost all the reagents across this oil phase. Whereas if we lowered the pH such that the two molecules were neutral, you had nearly no transport again across the oil phase. And to me, that indicated that actually you get the transport when the surfactant and the encapsulant attract each other. And we showed through many more experiments that it's electrostatic or strong van der Waals interactions that must occur between the two types of molecules for the transport to occur quickly. But as soon as you have some repulsion between them, you have nearly no transport again throughout the show. This we summarized in this plot here where the retention factor is nothing else but the product of the average charge of the surfactant and the encapsulant. And as long as that is negative, so you basically have an electrostatic attraction, you get a very fast transport. As soon as that factor is positive, so you have electrostatic repulsion between the two types of molecules, you have nearly no transport anymore. And that is actually quite a nice way to selectively transport molecules across the oil shells. And then also to suppress these oil shells. The other method that is a little bit more, I'd call it engineering approach, is that you minimize or reduce the number of drops that form within these oil shells through the dimensions of these double emulsions. For these small drops to form, you need some sort of a convective flow. And if you increase the hydrodynamic resistance within the capsule shell by making this shell much thinner, actually you reduce the convective flow within them. And the hypothesis was that then you slow down this transport. And to reduce the thickness of these double emulsion drops, we designed what we called aspiration device, where we inject these double emulsions into a device where the main channel is intersected by many small shunt channels that are fluorophilic. And these shunt channels are connected to reservoirs that are at and under pressure. So what we basically do is, like in a Hoover, we suck out the oil from the double emulsions. And actually there we can suck out up to 95% of the volume of this oil, getting double emulsions that have shell thicknesses of around 300 nanometers at the throughput of, again, about 1,000 drops per second. Now, by doing that, we could actually indeed reduce the permeability of the shell towards fluorophore. As you can see here in this movie, I'll play it again. Sorry. Here you have a double emulsion with a shell thickness of around 10 micron, this is 300 nanometers, and you see that the one with the thinner shell leaks significantly slower. And that is counterintuitive if you just think about the diffusion. But if you think about the formation of these small drops, actually it becomes more intuitive. So these are the two possibilities. Either you chemically modify the surfactant that we came up with, either you modify the surfactant to ionically cross-link it, or you choose the engineering approach and make the shell thinner. One thing that we wanted to do, which also was very much inspired by the really nice work of Laura on the vesicles, is to completely remove the oil, because if we completely remove the oil, we wouldn't have this issue on transportation anymore. This is something that we failed. We never managed to remove all the oil from the shell. We only could remove 95% of this oil. And so to me, this is why we gave up a little bit this round, because I couldn't see how we could make that, how we can get the control that I wanted to get with this technology. But since we could get it with these functionalized surfactants, we pursued this route. And we actually looked a little bit further. We started to cross-link the shell with ions, with iron, and looked at how this ionic cross-linking of the shell influences its mechanical properties. And as you can see here in this movie, you form shells. I don't know if you can see it, but you see a very thin shell that wrinkles here at the drop. And if you put the two drops in contact, you actually see that the two shells merge and you get a fluid exchange, which indicates that these shells are viscoelastics. This you can also see on this movie, that you have something solid, viscoelastic, that you see forming. And to just monitor, to show that it's actually viscoelastic and that you can exchange reagents between the two different drops, we trapped an air bubble in the sessile drop here. And as soon as the neck that forms between the two drops is large enough, you can exchange this air bubble. You can then separate it again, and they self-heal because of their viscoelastic properties, because the surfactants are only ionically cross-linked, not covalently cross-linked. And of course, if you ionically cross-link, you completely suppress the transport of any reagents across these shells for as long as the shell is stable, which depends on the pH and the ions that you use to cross-link. But this is then, to me, the safer method to completely suppress uncontrolled transport of reagents across oil phases on the long term. Now, this is, again, on individually dispersed capsules. But if you remember what I told you in the very beginning, we actually would like to use these capsules as individually, as building blocks to generate more macroscopic materials, okay? But what we also saw is that if you use this first generation of modified surfactants that allow us to form these viscoelastic shells, these shells are relatively weak mechanically, so we can't really up-concentrate them without compromising their integrity and stability. And we could not really control the permeability of them either, because we think they're just too defective. And if you think about the structure, you wouldn't expect these kind of surfactants to form well-defined layers, because they have only one ionically cross-linkable group per molecule. And to get percolating networks, you need at least two, actually better three. But just for chemistry reasons, 3 is even more complicated than 2. So we made a second generation of surfactant that has 2 such Catechol derivatives per molecule. And we ionically cross-linked them, and we could immediately see that these shells are a lot more stable. And actually now we can tune permeability of these capsules quite well by changing pH and the type of ions. A big advantage of this technology, in my view, is also that now we don't need double emulsions to make these capsules. We actually can make them from single emulsions. And the reason that I think this is a very big advantage, especially for the application we have in mind, is the throughput. If you think about the throughput, the formation of these double emulsions of well-defined dimensions, we get about 1 gram of capsules per hour, which is good enough for some lab applications, but it's definitely not good enough for building macroscopic materials or even industrial applications. If you in contrast can make capsules from single emulsions, well, you can easily scale up by a factor of 100 without compromising the control on the size. And if you don't care about the size, you can emulsify in bulk with bulk methods, and then you can easily produce even kilograms of these capsules per hour. So then scalability suddenly is really not an issue anymore. And that was a big advantage, and to me also a game changer in terms of using this technology for fabricating macroscopic soft materials. So that's what we did then. We started doing single emulsions using a device that I again developed as a postdoc in the lab of Dave Waits. We call it the millipede device because it has about 1,000 nozzles. Because the drop size is independent, or nearly independent of the fluid flow rates, you get very well-defined drops at the relatively high throughput, so up to 100 milliliters per hour, depending on the viscosity of the interface. Now, what many people do with these drops is they convert them into microparticles by basically having an interface, an aqueous phase that contains reagents and some sort of initiator, then initiating the polymerization reaction, for example, through illumination with UV light, and then you transform these drops into particles that have similar sizes as the drops are. We did something very similar with an important difference, though. We produced the drops in exactly the same way. We deposited them on a substrate, but then we let the surrounding oil evaporate before we initiate the polymerization reaction. As the oil evaporates, the drops deform because they want to minimize the interfacial area between the drops and the air. So they become hexagonal prismatic particles. And only at this point, we started to initiate the polymerization reaction, with the result that the polymerization reaction was not completed when almost all the oil was evaporated, such that basically these interparticle connections were lost. And so we used the rest of unreacted monomers to covalently connect these adjacent particles, and what we got is integral microgels, which had very well-defined micrometer-sized patterns. So we could tune, of course, then the microstructure by tuning drop size and the arrangement, and we could tune the surface roughness by controlling the polymerization kinetics of these monomers. And we could then abruptly change the composition of these hydrogels by mixing different types of batches of drops that have the same size but different compositions. Now, if you look at these patterns and you look at the skin of lizards, you see some striking resemblance, with an important difference, I think. Here, in our system, we cannot determine whether this particle, for instance, is black or green. This is just random. I don't think nature assembles these tiles in a random way. And to gain a better control over local composition, we actually designed microfluidic trapping devices that have different trapping strength So basically the way that it works is you have a thin chamber whose height is smaller than the diameter of the drop. So the drops are squeezed. And within this chamber, you design traps where the height of the channel abruptly increases. And as soon as the drop hits such a trap, it can relax, it can expand into the height in C direction, and thereby it reduces its surface area and thereby surface energy, and that results in a trapping force. And as long as the shear force that is applied to the drops by the surrounding fluid is lower than this trapping force, the drop stays put. As soon as the shear, the drag of the fluid is higher than this trapping force, the drop is removed. And we took advantage of this feature. We studied how the size and the shape of these traps influence the trapping force, and we took advantage of that to design different types of traps to actually control which drop goes where. And thereby we could gain a true control over local composition of our hydrogels. But even though we could get this local control over the composition, once we mechanically tested our hydrogels, we were a bit disappointed because they broke again in a very fragile manner, because the interparticle connections here, they were weak. And actually, I don't think they were weak, but the polymerization, the cross-linking density was just so low that actually we broke them very rapidly. Now, what does nature do to increase the toughness of this kind of material? It introduces reversible bonds that can dissipate energy. And if you think back on where I stopped with the capsules, with the viscoelastic capsules, we thought, well, we could use them as glue to increase the toughness of these kind of materials, right? So we could basically use our interfaces here as glues. And that is what we did. We did it first in 2D. We showed that you get self-healing properties of these kind of films in 2D. And then, of course, you can do the same thing in 3D. This was very preliminary results, but we showed that we can extrude them and that actually the granular structure is retained, even if we have these viscoelastic shells that basically are still filled with the liquid. So it's not a real solid material. It's more like a foam-like structure. How can we convert that into something load-bearing that I really would like to get at the end? So how can we connect these particles more strongly to each other? And I have two very talented PhD students who had a very good idea. They thought, well, let's go a step back. Instead of using these capsules, let's use simpler, the microparticles, the hydrogel-based macroparticles. And actually, each hydrogel has a sponge-like property because it's a polymer network that is filled with a very high fraction of water. Now, if we load them instead of just with pure water, with water containing some reagents, we can actually store a lot of reagents within these particles. So they made these hydrogels, incubated them in an aqueous solution containing their reagents, and then they jammed them. Jammed is nothing else but up-concentrating them. And because these soft particles, they are so soft that they start to deform when you concentrate them up, they start to then behave not like a liquid anymore, but they start to behave like a solid, like a shear thinning paste, which actually has quite well-suited rheological properties for extrusion-based bioprinting. So they actually printed these kind of particles into macroscopic structures. Here is just rheology that shows that you have very fast shear recovery, which you need for 3D printing, and the shear thinning behavior. They 3D printed them. Of course, the granular structure was retained because the hydrogels, they don't break during this process. But what was, and this has been done before, this is nothing new, but what was new is that here you still have these unreacted reagents within these particles, and we use them to perform a percolating network that interpenetrates the particles and covalently cross-links them. And the important point is that this step, this cross-linking step, happens after the 3D printing process has been complete. So you don't form weak connections between subsequently deposited layers, but you get integral percolating 3D network that imparts the strength and stiffness to the material. Just quickly to show you how you can 3D print this, you can do macroscopic centimeter-sized structures, and because of the 3D printing ability that allows you to locally change composition, you get shape. We can design shape morphing materials. because of this percolating network that is isotropic, we do not have the mechanical properties are isotropic as well. So we do not see an influence of the printing direction on the mechanical properties of our 3D printed materials, which is something that is quite unique for 3D printed polymeric materials. And because now we connect these particles, well, not only through their interfaces, which has been done before, but through a percolating network that distributes the stress much more homogeneously, we actually could increase the stiffness of these materials by at least a factor 4. So we could really use it for load bearing applications under tension as well as under compression. Now, if you think about these materials and we think about sustainability of materials, which becomes increasingly important, I thought, well, this would be that is a material that is actually quite well suited for recycling, because as soon as you decompose the percolating network, materials will disassemble it into individual building blocks, into particles in this case, and you should be able to recycle them. To show feasibility, we formed a percolating network that is formed through disulfide bonds that can be hydrolyzed through the addition of some chemicals to be decomposed into its individual building blocks. And by doing so, you can actually recycle the material within a couple of minutes to hours, depending on the conditions that you choose. We showed that neither the biological properties of the ink nor the mechanical properties of the hydrogels strongly depend on the recycling. So even if you recycle it, you don't weaken. If anything, you strengthen the material, which is one of the major limitations of the recycling of some of the most commonly used plastics that become weaker and weaker with recycling. So we really don't suffer from that. Why? Because the particles themselves, they remain integral. And so we could recycle these materials over and over again. Now, hydrogels, they are inherently limited in terms of stiffness and strength you get. And just to demonstrate feasibility, we showed that if you now dry these hydrogels to get a dried polymer, you actually increase the stiffness by a lot, and that by itself is not very surprising. But what was nice to show is that we can, even if after drying, we can then recycle them within a couple of hours without compromising the mechanical properties of these materials. And just to show a full proof of principle, my PhD students, they cast a wrench with the wrong size dimensions. They recycled within a couple of hours, cast a new one that was able to then help tighten a bolt made out of metal. Showing that actually the mechanical properties of these materials are pretty good. And with that, I'd like to conclude. I hope I could show you that by controlling what kind of compartments you make, the surface chemistry of the compartments, I really think that you get a lot of possibilities to tune local composition and mechanical properties of macroscopic granular materials. And I also hope that in the future, we can leverage this granular structure and the properties of the capsules themselves to selectively release different types of reagents to then design truly functional materials that hopefully in the future can be used for load bearing applications. With that, I'd like to thank my group for all the work. They did all the work. I didn't do anything of that. Thanks a lot again, Laura, for giving me the possibility to present to you, and I'm happy to take any question you might have.
Thank you very much, Esther, for this very, very nice talk. I really enjoyed. And now we have time for questions from the audience. You can directly unmute yourself if you have any question for Esther. Otherwise, I will break the ice. Esther, about this last part on the material itself, on the assembled material, how long can you store that material, or it would be possible to dry it and later make it swell and restore the properties?
That is a very good question. Actually, yes. The way that we produce them, we produce the microparticles and we dry them, and then we can store them forever, and we can swell them whenever we want. But even in the swollen state, it is still a hydrogel. So, I mean, we haven't tested it for years, but at least for a couple of months, this remains stable, and we haven't seen any change in mechanics at least.
Beautiful, very promising. Any question?
Yeah, may I ask a question?
Sure, go ahead, Walter.
Did you measure fracture toughness?
Yes, we started measuring fracture toughness. And there, we must say that there is still a lot of potential. The fracture toughness of our granular material is higher than that of a double network bulk unstructured material. But the fracture toughness of this kind of hydrogels is inherently relatively low. And there is where I think there is still a lot of potential to actually improve and improve this material by changing the type of the material that you use to make the percolating network, for example.
Okay, thank you.
The toughness is inherently limited by the very limited stretchability.
Yes, okay, I understand.
Any other question? Esther, in which range can you vary the size of the droplets to make still the raw material?
That is a very good question. I mean, as you know, for microfluidics, we can vary it in a conveniently between 50 and a couple of hundred micrometers. We recently introduced what we call surface acoustic wave-based emulsifier. There we make airborne drops first, and then we immerse them into an oil by taking advantage of positive spreading coefficients. And there we can go to drop sizes between 1 and 10 micrometers. So there we gain an order of magnitude, more or less, which I think is important. Going lower than that, we still failed. So if you really want to go lower, we use tip sonication, but then of course you're very broad in terms of size distribution.
Mm-hmm.
Yeah.
Okay. Yungwei, do you want to ask?
Yes, yes. Hi, Esther.
Hi.
I have a question. The granular hydrogels are still somewhat spherical, and that they are interconnected. And but if you make them, can you make them completely non-spherical, and then they interlock themselves? And another comment is, what about adding some load-bearing like composite material that take the stress in another way, like two different components?
Very good questions. Two very good questions. First question, that is what we started recently, a couple of months ago, making non-spherical particles. And actually the reason was not that we wanted to make non-spherical particles, but the reason is that some of my PhD students really would like to try to commercialize this. And to gain in scalability, we decided to buy a cryomiller where we start with bulk hydrogels and then we just mill them into small particles. We get a reasonably good control over the size. Of course, that's by no means as monodispersive with microfluidics, but it's reasonably well defined. But you get very non-spherical particles, very fragmented particles. What we see is that basically the rheological properties change a lot because the rheological properties depend a lot on the shape of these materials. So the whole jamming process, the protocol for jamming needs to be adjusted. But as you correctly mentioned, the mechanical properties, they are usually superior if you have non-spherical particles because they interlock. Absolutely. And I think there is still a lot of things to be discovered, and also a lot of different types of materials to be included in these kind of studies to get a better idea on that. Now, the interlinking, again, a very, very good question. And this is something that we're currently working on. One is using nanoparticles to strengthen, which works reasonably well, but the work is still not in a state yet where I dare to present it. And the second thing is that we exchange the hydrogel by other type of polymeric materials that are just stronger and tougher. And this is, again, something we're currently working on, which shows very promising results. Again, it's not yet in a state where I dare to present it.
Okay, cool. Looking forward to the new results.
Thank you. Any other question for Esther? Okay, Otherwise, I would like to thank Esther again for this very, very nice seminar, and all of you for your participation today. And please join us again after Easter